NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Good evening. My name is Sarah Marcotte from the Mars Public Engagement Team. Curiosity, the rover that successfully landed on Mars in early August 2012, has been busy refining much of what we know about Mars. Gale Crater has presented the rover with rich new environments to study, such as ancient stream beds and shifting sand dunes. With a suite of 10 science instruments, the rover and science team have been working to reveal the answers to existing questions, while, of course, generating new ones. This talk will revisit the successful landing and reveal some of the results from the past year of work on the surface of the red planet. Tonight's guest holds a Bachelor of Science degree in geophysics from UCLA and a PhD in planetary science from Caltech. His research interests include the climate history of Mars, the weather on Jupiter and Saturn, and the possibility of ice at the poles of our moon and of Mercury. He has participated in the operation and analysis of data from several NASA missions, including the Lunar Reconnaissance Orbiter and the Cassini mission to Saturn. Currently, he is a planetary scientist at the Jet Propulsion Laboratory, where he is deputy project scientist of the Mars Science Laboratory mission. In this capacity, he leads an international team of over 400 scientists. Ladies and gentlemen, please help me welcome our speaker tonight, Dr. Ashwin Vasavada.
All right. Well, it's wonderful to be here. It has been a wonderful year and a little bit of an exhausting year, honestly. But I'll tell you all about what we've been finding on Mars and kind of just walk you through what the last year has been like for us, starting with the wonderful arrival of the Curiosity rover at Mars more than a year ago at this point, and then all the scientific discoveries we made along the way. So I'm looking forward to talking with you about that. But before that, I want to take us all back to August 5th last year, about 10:30 p.m., and even the time before that, all the work by so many different people that went into getting this rover to Mars. So let me get up a little movie. You can all watch me do it.
That great things take many people working together to make them happen. is one of the fantastic things of human existence.
Not only have we driven the rover, we've removed its arm, put it all through its paces, but it's been in a thermal vacuum chamber and kept very cold. Parts of it have been in a centrifuge. We've done drop tests, pull tests, drive tests, load tests, stress tests. It's just an amazing amount of testing this vehicle has gone through. We've tried every way of operating the vehicle using the software, literally thousands and thousands of hours of software testing. It's been just an amazing several years, really, of constant testing and development, finding problems, fixing those problems, and going on to the next problem. I think she's ready to go.
LC, this is the LD on channel 1. LC, you have permission to launch.
Roger. Proceeding with the count.
T-minus 10, 9, 8.
7, 6, 5, 4, 3, 2,
1.
Am I confident that she's going to go and she's going to be successful? Absolutely. It's going to go and she'll be good.
We should have parachute deploy around Mach 1.7. The parachute is deployed. We are decelerating. Feed shield has separated. We're found the ground. Standing by for back shell separation. We are in powered flight. We're at an altitude of 1 kilometer descending. Standing by for sky crane. Sky crane has started. Touchdown confirmed. We're safe on Mars. Time to see where our Curiosity will take us.
What a fantastic demonstration of what our nation and our agency can do. I could only think of the words of Teddy Roosevelt as I was sitting there. It is far better to dare mighty things even though we might fail, than to stay in the twilight that knows neither victory nor defeat. And the team brought us victory today.
Today, right now, the wheels of curiosity have begun to blaze the trail for human footprints on Mars. This is an amazing achievement.
Well, today on Mars, history was made on Earth. The successful landing of Curiosity marks what is really an unprecedented technological tour de force. It will stand as an American point of pride far into the future.
We've got a long mission ahead of us, and because of that and the capabilities of this rover, we have this possibility for just monumental science accomplishments.
Within 2 months, the team found an ancient riverbed, evidence of flowing water.
We have found a habitable environment that is so benign and supportive of life that probably if this water was around and you had been on the planet, you would have been able to drink it.
Hardest part about giving talks like this is watching that video and being able to speak after it. Yeah, I started working on Curiosity in about 2004. And at that time, there were already maybe a few dozen people. We then expanded up to over 1,000 people here at JPL. And as Sarah said, over 400 people around the world being science team members, and even hundreds of other people at different NASA centers and at other firms like Lockheed Martin, who helped make a good part of the spacecraft that took us to Mars. So if I had to summarize 10 years in 2 slides, it would go something like this. For the first several years, this was the challenge. I'm a scientist, of course, and so I came here having mostly spent all my time in research, although I worked with these beautiful spacecraft like Cassini, but never so close to the engineering teams that build and design and test these spacecraft. And the challenge for MSL, for Mars Science Laboratory, which we now call Curiosity, was to get a 1-ton rover to the surface of Mars with the most sophisticated science payload that had ever been conceived, and do one of the most ambitious scientific research projects you can imagine, which is to figure out if Mars could have ever supported life. Just getting there was a great part of the challenge, and the engineers considered all kinds of different approaches, landing on airbags, landing with retro rockets, all these different ways we've landed on planets before, and the most efficient way to deliver this one-ton rover to Mars was this contraption. And this was the reaction when we told it to our bosses at NASA headquarters. And this was the reaction every time I show a video of that in the last decade to the public. And honestly, this was the reaction of a lot of us here at JPL, including the engineers who designed this on paper and in all their computer simulations, because a lot of the challenge is that there's nowhere to test this. The first time this ever was tested end to end with everything working together was on August 5th of last year. And so no way. And yeah, I mean, this is just the product of these amazing people who, this is the team that brought Curiosity from Earth to Mars and then landed it. So, this talk is dedicated to them. But I'm a scientist, so we're here to talk about science. And for the next hour, we'll go through that, and we'll tell you all the things we've done since this wonderful group of people brought us to Mars. Here's sort of the thing that drives this mission. Mars resembles Earth in many respects, especially in its early history. And in fact, if you look at Mars, just took you back 3 billion years, Mars may have looked like this. It may have even had an ocean. For certain, it had a thicker atmosphere. We're pretty sure of that now, thanks to Curiosity in part. And we have lots of geologic evidence for rivers flowing on the surface, for lakes, and for a pretty active hydrologic cycle. If all those pieces are in place and Mars was so Earth-like, of course, the natural question is, did Mars ever support life? We've looked for life on Mars with spacecraft before, and it's pretty difficult. In fact, the more we study life on Earth and how life evolved on Earth, it sort of goes in two different directions. On the one hand, we keep discovering more and more forms of life on Earth that can live in extreme environments, which sort of makes us think, why not Mars? Mars is so Earth-like, it's just sort of a more extreme environment than Earth. But on the other hand, the more we study evidence of life on Earth and search for it in billion-year-old, 3 billion-year-old rocks on Earth, the more we realize it's pretty hard to detect. So if you were to go to Mars and pick up a 3 billion-year-old rock, even if you were to go to Canada and pick up a 3 billion-year-old rock, when we know there was microbes all over Earth, it's pretty hard to tell life from other things that look like life once it's been around and degraded so much. So Curiosity chose a different goal, which was to ask this question instead. Was Mars ever a habitable planet? It's more of a practical problem. It's one we could put our arms around as geologists on this mission, and even actually working with a lot of paleontologists in the Earth community that help us figure out how to answer this question. So we're not looking for life with this mission. We're looking for answers to whether Mars could have ever supported life. And that's the goal that NASA gave us. This was sort of the initial instructions we had from NASA headquarters back in 2004. Curiosity's prime scientific goal is to explore a local region on Mars' surface as a potential habitat for life. And what does it mean to search something as a potential habitat for life? We can look at a few different things. We can look at its biological potential. Does it have the basic ingredients of life, such as carbon and water? What about the geology and geochemistry? Are there certain environments where we know that life thrived on early Earth and even thrives today? Lakes and places where water concentrates, especially fresh water. We want to study the water and weather. Even today, Mars has water in its atmosphere, but in the past, it had these rivers and lakes and possibly even an ocean, a much more vigorous hydrologic cycle. And then, of course, we want to look at the other side of the equation, which is the hazards to life. What would cause Mars not to be a habitable planet? So we have instruments on Curiosity that look at radiation, for example, ultraviolet light, as well as high-energy atomic radiation. So we outfitted this beast with 10 scientific instruments that cover all these bases of what I just described to you in the science we're trying to do. And it took this giant rover to carry all those instruments to Mars to answer that breadth of questions about habitability. You simply couldn't have done it with a smaller rover. So that was the challenge scientifically, and it turned into the engineering challenge of landing this thing on Mars. So we have a mast with eyes, beautiful HD color cameras. A lot of the pictures you'll be seeing tonight are from them. We have an instrument on the top here that shoots out a laser at rocks and is able to create little sparks on rocks and look at the color of those sparks And the color of those sparks tells you the composition of those rocks and soils. So from up to 20 feet away, we can just zap rocks and soils and do a quick survey of what's around us. That really helps us to then zero in on places we want to go examine more closely. We do that with this 7-foot robotic arm. That arm has what we call a turret at the end of it, which has a microscopic camera, so we can take very close-in images of a rock or a soil, just like a geologist would do with a magnifying lens here on Earth. We also have a spectrometer at the end of the arm, so we can place a sensor on a rock or soil, get a detailed chemical reading. And if things look exciting after we've gone that second step, the real critical capability that Curiosity has that nothing had before is to actually sample the inside of that rock, to drill into the rock, gather powder from that rock, and deliver that powder into laboratories on board the rover. So the entire front end of the rover here and about a third of the way back consists of 2 state-of-the-art scientific geochemical laboratories that we can deliver samples of rocks and soils into. And then we have even more instruments, and you know, in talks like this, I can't even get through all 10. It's a wonderful payload, and here they are listed. But one thing I do want to remind you is that before we were called Curiosity, as a naming contest that Clara Ma, a 6th grader from Kansas, won and named us Curiosity, we were formerly known as the Mars Science Laboratory. And that's because, as I mentioned, we have these wonderful scientific lab instruments in the front end of the rover. This is how big they are. That one is the size of an old 1970s microwave oven. It's a very sophisticated mass spectrometer and tunable laser spectrometer, and I'll talk a little bit about what it does. And this one, which is out, is a sort of a field instrument that one of our principal investigators is carrying around. It's called an X-ray diffraction experiment. It's the state-of-the-art way a geologist determines what minerals are present, even on Earth. So we took this instrument and put it on the rover, and we took what usually fills up an entire laboratory at a university, compressed it down to the size of this box, put a little gold plating on the side to make sure you know it's expensive, and then we put it inside the rover. But before we can answer all these wonderful questions, you have to ask, where do you go? That's another challenge of missions like this. You only get to go to one spot. If you had to tell your alien friend where you'd go on Earth to figure out everything you want to know about Earth, or ancient Earth life, or how we got to be here, you know, would you go to the Mojave Desert? Would you go to Canada? Would you go to the middle of the ocean? We have to search all of Mars to find that one spot where we can send this multi-billion-dollar, 10-year effort to. So we did that. We spent about 5 years scouring Mars to find the perfect landing site, involving hundreds of scientists around the world, meeting in hotel ballrooms for once a year for 5 years, hashing it out. It was pretty fun, arguments at times, but it was good. And here's the one we chose. It's called Gale Crater. It's an impact crater. So a long time ago, something huge hit Mars and tore this 150-kilometer hole in the ground. It then later filled up with sediment. Something, probably wind or water, filled the whole crater up. And we don't know how that happened, but that just tells you Mars has had a pretty vigorous history, and we're just seeing the remnants of it today. But this whole crater, which is about 5 kilometers deep, 3 miles deep, filled up completely, and then something else over another hundreds of millions, billion years, eroded a lot of that sediment away, leaving this central mountain in the middle of it. And we know it formed that way, and it's not a volcano, and it's not some other process, because when we look at it with some of our cameras from orbit, we realize the whole mountain is made up of rock layers, basically flat rock layers. This is what really drew us to the site. If you're a geologist on Earth, you love layered rock, like the Grand Canyon, because layered rock is a record of time. The older layers are known to form first, unless something really catastrophic turned it all upside down. Not on Mars, probably. And then as you go up and up, you get younger and younger in history. And what made this attractive was the discovery that this mountain was made of layers. What made it even more attractive and really into a winner was 2 other things. The first is, when we looked at the rock layers from orbit, we found that they not only vary in their texture and color, they vary in their mineral composition. The bottom layers are made out of clays. Here we're looking at this layer here. And then as you go up the mountain, there's layers made out of a mineral called the sulfate. Now, to make a long story short, when we think it was a lot wetter on Mars, when a lot of fresh water interacts with the kind of primary rocks on Mars, you would expect clays to form, just like on Hawaii. A volcano erupts, you get that nice, fresh, black lava. Over time, it turns into clay soil. That same thing would be expected to happen when Mars was a lot more like Earth. As the water was drying up on Mars and disappearing, you get a little bit more dissolved things in the water. Volcanoes are going off, putting sulfur in the atmosphere, and you might get sulfates. And then the entire upper half of this mountain is made up of just boring Mars dust. The unique thing about that is it really fits what we think Mars' entire history was. We think that the earliest time had a lot of this fresh water around, although we weren't sure of it. Then we think Mars transitioned to where the water was being lost and a lot of sulfates should have been forming as the water would evaporate. And then the most recent half of Mars history is just a desert, cold planet. And all it's doing is wind blowing around, eroding rocks, and creating dust. So this mountain may contain the entire geologic story of Mars. And if we can climb it, if we can drive over to it, check out those bottom layers, which may be the oldest history of Mars, drive up through the sulfates, look at the water being lost, and then get to the dusty layer about halfway up, we can hopefully really piece together for the first time in a really solid way the entire geologic and environmental history of Mars. So it's a cool site. The next thing we discovered, though, which is just sort of fortuitous, is that there's a river coming down the crater wall and spreading material across the floor. It's all dried up now, probably has been for a couple billion years, but at some point there was a river flowing and creating a little fan across the floor. And it turned out the best place to land, since we can't land on the mountain, we have to find a place that's relatively flat, about that big to land in. And we found that the best place to land was just right on top of this fan. So even if the mountain turned out to form in a different way and sort of our hypothesis didn't work out, we knew we had a chance of being near a feature that did form in water. And so this just made a great site for us. Well, here's when we got there, August 5th. This is a descent movie that we took with one of our cameras that's mounted looking down on the rover. So this is now when the rover was hanging, inside with the rockets firing and flying down to the surface. And the heat shield separated and fell down to Mars. This heat shield took us from space into Mars' atmosphere when it gets really hot and you have to burn off a lot of friction. We got rid of it once we got inside Mars' atmosphere, and this is a frame of the movie that is taken as it's falling away. And just like Hollywood, have you ever seen when photographers have to have that little white balance card to make sure the colors come out right? We were filming a movie on Mars, and this piece of cloth here was there to make sure we understood the white balance of these pictures. True story. Okay, and then I just took this other frame from the movie because to me, it brings back all these memories. When I was a kid watching the Apollo landings, I didn't watch them, but when I was later a kid, seeing the stuff you guys saw. No. I watched those movies so many times as I was growing up, and this just reminds me of those final moments as they were landing on the moon. We had our own moment like that last August. This is, I think, the second picture. The Curiosity got back from the surface. And this is the words that my friend Alan Chen said as he called the landing on the movie that you just saw. He said, "Touchdown confirmed, let's see where Curiosity will take us." And I love this picture because it kind of set the tone for the whole mission. We count ourselves very fortunate, of course, for how everything had turned out. And one of those things where we got the feeling that it was going to be a pretty cool year was when this picture came down. We had no control over which way we landed on Mars. And of course, we didn't really plan any of this, but when we got the picture, we saw Mount Sharp in the background here, this mountain in the middle of the crater, our ultimate target. Got this beautiful shadow of the rover. You just couldn't set up the mission better. Afterwards, we took a couple days to deploy our mast, which has the cameras on it. We landed with it fastened to the deck. So it was a big moment for us when we saw that the mast had deployed and our cameras started taking these beautiful color pictures. And this is Mount Sharp in color now. You can see the dusty layer. The clays and sulfates are in here, and the black line is some dark sand dunes that sort of encircle the mountain. What we noticed, though, after landing, and again, we had never landed, of course, with this system before, so it was sort of new, is that the rocket engines, even though they were some 40 feet off the ground, picked up a lot of this gravel and created a couple marks on either side of the rover. So 2 engines firing on either side, and they created what we call these scour marks. And so we, of course, as scientists, the first thing people wanted to do was go check those things out. And so we did. We took some telephoto images. We weren't quite comfortable deploying the arm yet or doing any of our advanced capabilities just a few weeks after landing. So we took some high-res pictures and then just kind of moved on. But these pictures were pretty interesting because they revealed that the gravel that we landed on didn't go very deep. In fact, only a couple centimeters below where we landed, there was bedrock. It was strange-looking bedrock. We sort of puzzled over this, but kind of didn't know what we were looking at, really, so we moved on. But you can see that it looks like a bunch of different rocks kind of stuck together. Doesn't look like a massive piece of bedrock. So that was a little puzzling. But then we got out of there. And this is a map now looking down from space. Bradbury Landing is named after Ray Bradbury. We dedicated the landing site to him. And the rocket engines blew dust off of a whole area about 100 meters on either side of the rover. So we kind of cleaned off Mars temporarily. I'm sure it's dusty again. And then we drove out of there. And we decided, well, here's the funny thing. Mount Sharp is this way. So why do we drive that way? Good question. So we drove that way because remember that fan I told you about, the river coming down, spreading material across the crater floor? We really wanted to go see what that was about. And it turns out we landed just off of it, maybe about 400 meters away from the edge of that fan material. And so we thought, hey, let's go check that out. I think we were up here in Von Karman giving a press conference. We said, the project scientist who I work with, he said, well, we'll go check this out. The team wants to go see what this fan material is about, and we'll turn around by around Christmas. And this was August, and I thought, Christmas? You got to be kidding me. We should just go over there for 2 weeks and, turn around. We actually turned around on July. So yeah, but you'll see why. So we drove the wrong direction, and we drove over to this place where this fan material comes down. And it turned out we found a place where 3 different terrains all come together. The fan material, which we call this fractured unit, the material we landed on, this gravelly, hummocky unit. Hummocks are just kind of hills. And then this cratered unit. There's a lot more craters here, meaning for some reason that little patch of ground is older than the rest and has had more time to collect craters, or at least has not had them wiped away by some other process. So we drove over there, and it took a few months to get over there because we stopped a few times on the way to test different things out. This is a very complex rover, so we actually had planned sort of breaks in the science campaign where we would stop for 2 weeks, test the arm out, stop for 2 weeks, test the scooping out, stop for a month, test the drill out. So it kind of extended things, and we got over there by about the end of about 2 or 3 months into the mission. Along the way, though, we started seeing more of this stuff. We started seeing more slabs. Now, this wasn't even buried. This was just sort of sticking up. We were driving. We took some pictures one day, and here was this thing coming out of the gravelly ground that looks a lot like a sidewalk, broken sidewalk. There's no trees. There's no bad, city maintenance around here. But it was very exciting because now we could sort of see in cross-section, what the stuff we saw exposed by the landing engines. When we looked at it in detail, it's a rock made up of a lot of other rocks. And geologists call this a conglomerate, when a rock made up of a bunch of smaller rocks cemented together. And what's even more interesting is that when you looked in detail at the rocks in here and then the ones that have presumably eroded out of it, they were rounded. Now, we'd never seen rounded rocks on Mars before. You see these jagged things that come when an impact hits and you shatter rock. We see all these little rounded 1 centimeter-ish stones. That was, to the geologists on the team, there's only one, the number one process you'd go to on Earth to form that, you could probably guess. Right? I mean, you're probably reading my caption. But yeah, when you go to a stream or a river on Earth, and the water is transporting rocks for several miles, and they're all sort of rolling along the bottom and hitting each other, you end up getting a lot of rounded pebbles. And by the roundedness of these pebbles and then the size of them tells you how much water was there, because the more water, the bigger things you can carry. So by looking at the total picture here, they were able to conclude that we were actually driving over a stream bed. The Curiosity's wheels would have been buried, or whatever you call it, underwater if we were there a couple billion years ago. And so based on all these measurements, the science team came up with the conclusion that this indicates a stream bed environment where water once flowed ankle to hip deep, about several miles, which is consistent with that river coming from the crater rim that I pointed out earlier, and flowing a few miles per hour. So it's a real kind of gentle stream, the kind of thing you might go fishing in. And here we are seeing the first real evidence for flowing water on Mars. And just to remind you, this is where we aimed. We landed about here, and then this fan was coming down, and it kind of goes to about here, and we drove sort of to the edge of it. All right, so the hunt for habitable environments was on. But meanwhile, we did some other stuff. So for the next few minutes, I just want to walk you through 4 different little mini vignettes. One of the challenges now, even after a year, is that this rover with all of its instruments is doing so many different things. I'm going to offend half the team by not talking about their discoveries, and the other half of the team will be delighted. But that's the way it goes. So meanwhile, selfies. So one thing that's pretty cool is we have a camera at the end of our arm. The camera team had a lot of insight, actually. I didn't even see this coming, really, as we were developing it. The camera team was designing, of course, something that you'd put on a rock and take microscopic pictures so that the geologists and mineralogists on our team could look at the individual grains of the rock in detail and figure out where that rock came from. But what they did is they put a focus mechanism on that camera as well, so that they could focus not only on a rock a centimeter away from the lens, but they could focus like any camera. And so now we had a camera at the end of the arm. We could point anywhere. We could point on top of us, we could look behind us, we could look between our legs. And this was, it was actually a really neat thing, but this particular one is the first one we did before we even drove the first time, I think. Not the first time. Before we drove, we wanted to check out to make sure that the rover was clear of obstacles. And we do this regularly now. We actually peer under the rover if there's any danger that we might be high-centered, like a bad four-wheel driver. Another thing, though, is that they kind of surprised us again. This team is very creative and sometimes a little secretive. They went off and they figured out an incredibly complex series of moves with the arm to take a full portrait of the rover. Now, this sounds probably easier than it was. We don't have an arm as beautiful as a human arm. Roboticists are still trying to invent things as good as we came out. Our arm can do amazing things. If you were trying to do it, it'd be pretty easy. You could do it in 20 seconds. But it's sort of, I couldn't think of a good analogy for this, but it's sort of like scratching an itch on your back when you sort of have to kind of go like this, or, you have to like figure out the right way to get to any particular itch. And to take this portrait of Curiosity, they had to do that. They had to go through hundreds of different, ideas of how to move the arm around to take this self-portrait. And they did it one day on Mars, and it's just one of the most iconic images of the mission. And where's the arm? Well, of course, Photoshop, but yeah, now we regularly do this. It's good for kind of a documentation. So every time we do a major thing like drill, this is where we first drilled, and we took this self-portrait. We also did it where we first scooped, and we do it at every major milestone of the mission. It's a wonderful thing. It only takes like an hour or something on Mars to do, but it probably took them months to figure out how to do it. So the next kind of scientific story doesn't really have that much to do with cows, but only in the sense that it's about methane. And so methane, of course, is a gas that on Earth, a lot of it in the atmosphere comes from things like agriculture, and then comes from the insides of cows. Their stomachs produce a lot of methane as they digest their food, and actually it's one of the greenhouse gases. It gets a lot of notoriety on Earth. On Mars, it was claimed to be detected in the last decade by a few different groups of people. One was a European orbiter mission at Mars. Another were several telescopes from Earth that look through the Earth's atmosphere. And this would be pretty exciting, because if methane was on Mars, although there are different natural ways of forming it through mineral reactions deep in the ground, for example, delivery by comets and other things like that, one of the possible sources of methane on Mars would be biology. So we took a look at it. And I won't walk you through this whole thing, but this is just to say that the discovery of methane on Mars caused a lot of scientists to go do their homework, figure out how much might be produced by a lot of different sources, where it might be stored on Mars. And one of the answers they came up with is that if methane is produced on Mars today, it would only last a few hundred years. That sounds like a long time, but in geologic time, it's nothing. So that basically means if you found methane on Mars today, it's being actively supplied. Made the idea of biology producing it even better. But unfortunately, we took this beautiful instrument that shoots lasers between two mirrors and uses the very subtle absorption of light by methane to calculate how much methane was in Mars' atmosphere. And we brought this specifically to look at methane on Mars, and it turned out that we found nothing. So this was a little bit, I guess, disappointing, but as a scientist, I'm supposed to not let emotion play into it. We found no methane. But that's actually an important result. It kind of puts, at least temporarily, puts to rest this question of methane. We're going to keep looking as the seasons change, because maybe it actually changes with season. But so far, that's one of the, I got to be fair and tell you the bad scientific results as well as the good ones. Okay, the internet's wrong. Now that should be surprising to nobody. But if you were to Wikipedia the composition of Mars' atmosphere today, you'd actually find that 96% of it is CO2, or maybe 95 point something. Couple percent is nitrogen, and then maybe a little over 1% is argon. Well, we have this wonderful instrument, the one with the gold plating, that actually can measure the atmosphere composition as well. And we found that argon, with a lot more accuracy than anybody could do before Curiosity got there, argon's actually the next most abundant thing in the atmosphere after carbon dioxide. So it's not, life-changing, but on the other hand, it's rewriting the textbooks, and it's someone needs to update that Wikipedia page, so get on it. The other thing we found, probably more fundamental, is measuring what we call the isotopic composition of Mars' atmosphere. Isotopes are versions of molecules that have more neutrons than others. So it's still the same element. For example, hydrogen here. Most of the hydrogen in the universe has one proton and one electron. But sometimes there's actually a neutron, and that's called deuterium. And if you were to hold a glass of water on Earth that you got from the tap, 1 out of every 6,000 or so atoms of hydrogen would be deuterium and not what's called protium, which we normally call hydrogen. 1 out of 6,000. On Mars, when we measured this same number of deuterium, and as well as the isotopes of carbon and argon, we found that there's a lot more of the heavy isotope than the light one relative to Earth and relative to what we think is sort of what the planet's formed out of. So that means something is getting rid of the light versions of the atmospheric gases and retaining the heavy ones. And one of the main theories about how Mars went from a wet planet to a dry planet involves the loss of its atmosphere early in its history. And the mechanisms for losing the atmosphere over time, one of the favored ones is that the atmosphere is lost by the sun slowly stripping away, slowly eroding. The particles that are shot out by the sun into space slowly erode Mars' atmosphere over time. And that would preferentially take out those light elements and leave the heavy ones behind. So by measuring these isotopic ratios, we've really helped confirm one of the theories that's been around for a while now, but we've added a lot more sort of evidence to the theory that Mars lost a lot of its atmosphere early in its history. Okay, Houston, we have a problem, but NASA can solve it. The problem is not the lack of gender and ethnic diversity at JPL. And in fact, I thought I'd show you some of the fantastic women that I work with every day who run the rover, basically. And this is an event they did to get women into science and engineering careers, and they did a fantastic job. But the problem that NASA needs to solve actually is about radiation. So when we flew from Earth to Mars, we actually turned on our radiation experiment right after launch, and it measured radiation all the way to Mars. And there's a couple different sources of harmful radiation flying around in space. One is galactic cosmic rays. These are sort of things flying around from galaxies, and they're all over the place in space, and not a huge amount of them, but there's very high energy and harmful, cancer-causing, et cetera. Much worse for humans one day in space will be the particles that intermittently come from the sun, from coronal mass ejections, these big flares from the sun that spew particles into space. So we were the first we were able to provide the first measurements of these two sources of radiation from Earth to Mars, and then also, even kind of uniquely, from within a spacecraft, just the kind of spacecraft that humans will one day fly from Earth to Mars within. And the shielding of the spacecraft, the metal the spacecraft's made out of, actually changes that radiation in both good ways and harmful ways. So being able to measure it, Curiosity being in its little spacecraft, it's giant spacecraft, it could measure that radiation. And so this is what we measured from Earth to Mars. Here's the galactic cosmic rays. Here are the little spikes of solar events. And the reason it's a problem for Houston is that what we measured on Earth to Mars, when you calculate what an astronaut would take to go to Earth and Mars and back, it's more than the lifetime dose that NASA allows astronauts to get, which isn't a problem. It just means that NASA has to solve it. I mean, it is a problem, but NASA has to solve it. It's not a fatal problem. They have to just design spacecraft to shield their astronauts that much better. So we're contributing to future human exploration as well. Okay, when we last left our rover, we had headed for Bradbury Landing, over to Yellowknife Bay, and actually this is a picture, pretty awesome picture, from what's called the Mars Reconnaissance Orbiter, one of our orbiters at Mars. I think it's actually back in that corner over there, not the real one. And you see that giant telescope on that thing? That's kind of like launching half of the Hubble Space Telescope in orbit around Mars. Takes these fantastic images for us. Here's where we drove over to this edge of the fan, which we call Yellowknife Bay, and that actually is Curiosity as seen from an orbiter around Mars, and you can see our tracks. Yeah, so we can look at each other too, not just selfies. What we found as we got closer and closer to Yellowknife just got more and more exciting for us. We started going through this whole variety of rock layers that we didn't anticipate. We just hoped to find something unique in the fan material, but we actually found 4 different rock layers before that, each very unique in their texture and the environment they formed in. I can't go through all of them, but this is one of the more interesting ones. We started seeing these very thin platy rocks. If you've ever been to somewhere in the Southwest where there's a lot of sand dunes, you see things like this, especially in Zion National Park has a beautiful hillside full of rock that's etched with these fine lines. And that's actually a sand dune that traversed through there, then stopped, and then got turned into rock. And so we actually are seeing evidence of sand dunes on Mars, highly eroded now, but ancient sand dunes. When we actually went up to these sand dunes and looked with our microscopic camera, it turned out that the sand grains are much too big to be transported by even Earth's thick atmosphere. They're actually very large sand grains and require something more like water to transport them. So what we think we're seeing here is some other part of that river and stream system that was able to transport a large amount of sand and create ripples as it went. And so here is another piece of evidence for water. Here's what Yellowknife Bay looked like. This is the gravel we landed on, and then all of a sudden it turned into this much different terrain, these platy, flat rocks that were associated with this fan and river system we saw. We got deeper in there. We started seeing that the rocks were indeed made up of these plates, about 1 meter across usually. And you can see different layers. This is the bottom layer. There's another unique layer here. Those sand dunes are kind of up here. And so we were seeing a whole stratigraphy, a whole set of rock layers, each of which formed in a different watery environment. When we got closer, we used some of our other instruments, like our arm-mounted spectrometer and that laser that shoots the little spots on the rocks. And we found that the rock was heavily fractured with these tiny little cracks, but the cracks were filled with white minerals. And the white minerals, when we looked at it with our ChemCam, that laser, it turned out to be made of calcium sulfate. This is a mineral that can dissolve in water, and then if you run that water through rock for a long time, it'll build up and sort of fill the cracks with mineral deposits. And this is an example of that on Earth. So we found yet another way that water has interacted with these rocks, filling the cracks, having a lot of, leaving these calcium sulfate deposits behind. Another one are these little pimples. So some of the rocks had these things called concretions, which are other kinds of minerals that form in rock that's saturated with water, and water's flowing through and leaving minerals behind. So this sheepbed rock is the one that forms the bottom of Yellowknife Bay, the one that really we think is associated with this fan. And that's where we got very excited about seeing what we could find out with our big laboratory instruments that really we hadn't used yet for the first time on Mars in one of our main scientific questions. Now, this is a gorgeous image taken by our black and white navigation cameras of Mount Sharp in the background, the transition from the dunes to this upper unit to the sheepbed rocks of Yellowknife Bay, and the arm deployed with the drill in the ground, ready to do our first drilling. And we named this feature John Klein after one of our former deputy project managers who passed away shortly before we landed. So this is our drill holes. This is a little test hole. This is our main one. A dime will fit just around there. So we have a drill bit that's about a dime in diameter. We drilled in. This is the drill bit. And we were pleasantly surprised, really, to find that for the first time that any mission has eroded or scraped or drilled into rocks on Mars, the powder wasn't red, but it was gray. The interior of the rock actually had been protected from the oxidation that turns Mars red. And that's pretty key. That's the reason we brought a drill with us, honestly. I mean, we were hoping that the oxidation that's harmful to life, actually, and has turned most of Mars red, wouldn't have penetrated so deeply into the interiors of rocks. And we could find, if there's any evidence of life or the ingredients for life that would be destroyed by oxidation, by drilling into the rocks, we might be free from that. And so the fact that we got a scoop full of nice gray sand was a real wonderful moment for the team. We then, of course, needed to shoot it with a laser, because that's just fun. So this is the drill hole. These are the tailings that came out, and we kind of just zapped across, and we could get a nice chemical record of how the composition of the rock changes between the rock and the inside of the rock. And then here's another little, what we call a raster pattern, we can shoot with the laser as well. Well, I got to tell you what we found now, because this is sort of the biggest discovery of the year, and really the main reason we went to Mars in the first place. The lab instrument that's not the gold-plated one, the one that of the guy who was in the field using it, is called an X-ray diffraction experiment. It shoots an X-ray beam through a little sleeve of rock powder that we feed it after we drill. And the X-rays are sort of like light scattering in a prism. They form rainbow patterns because rocks are made out of crystals. And the unique rainbow pattern, there's a unique rainbow pattern for every type of mineral. So by doing this experiment on Mars, we can send back this pattern to Earth and figure out exactly what the minerals are in the rock sample. And when we did that for typical Mars sand as sort of a test, we got this beautiful set of rings, which turned out to be typical Mars basalt, typical Mars rock. When we did it on the John Klein drill powder, we got a very similar signature, except this bright inner ring. And this bright inner ring, believe it or not, grown men cry over this. No, joking. But it really was the thing that we were hoping to find. It's what we call phyllosilicates, which are basically a fancy word for clay minerals. And so finding these clay minerals and definitively detecting them with the state-of-the-art technique that geologists use on Earth was a big deal. This meant that water did interact with these primitive rocks and a long enough time. And the kind of fresh water that you heard Dr. Grotzinger mention in the intro video, the kind of fresh water required to form clays out of these rocks. So this was a huge discovery, and that leads to the story I'll wrap up with. When we put it inside the SAM instrument, the big mass spectrometer, it works a little differently. You put the dirt in an oven, and the oven slowly heats up. And as it heats up, different rock minerals begin to disintegrate, and they sort of let off vapor as they disintegrate. So this is another technique that's used very commonly on Earth. You heat up your rock sample, and you watch it disintegrate. And as it does, and you make a little chart of what comes off at every temperature, you can back out what it was made out of. And so that's what this is. I mean, you don't really have to know much more than that's what that is. And oxygen came off at one point, carbon dioxide, sulfur, water, and putting this all together, it revealed that the inside of that rock had both water sort of on the surface of it, just the thin amount of water that's in the atmosphere today, but also those clays. Those clays are known to break down at a very specific temperature, and then you see the water come off. And so the SAM experiment confirmed what Kemen saw, that these rocks were full of clay minerals, and actually detected sulfur and other things as well. So putting that all together, what did it mean? It meant that the team, after a lot of discussion and vigorous scientific debate, was ready to declare that Yellowknife Bay, at one point in Mars history, was indeed a habitable environment to the best of our ability to find it with these instruments. How do we make that conclusion? Well, the regional geology and the fine-grained rock of the sheetbed rock suggests that John Klein was at the end of an ancient river system or within an intermittently wet lake bed. We know that the river came down. We know that these rocks are the kind of rocks, that very fine-grained rocks that form in a lake environment when sediment being transported by a river has the opportunity to just settle down and then form into rock. The mineralogy indicates sustained interaction with liquid water. And based on all the different evidence of water I described, it wasn't too acidic or alkaline, and it wasn't too saline. There wasn't too much dissolved in it. Further, the big one, the conditions were not strongly oxidizing. SAM is able to look at a lot of different chemical elements and found a lot of the ingredients of life that life requires: carbon, hydrogen, oxygen, phosphorus, and sulfur. These are sort of on the top 10 list of what any biologist would tell you all of our cells are made out of and what life needs to survive. And finally, we're not 100% sure on this one yet. We're still working on it. But it appeared to be the presence of minerals in various oxidation states that would provide a source of energy. Let me break that one down for you, because that's a lot of jargon. But what it means is when you're looking for a habitable environment, you really, what life requires is the key ingredients for life: carbon especially, water, and food, a source of energy. And sunlight, of course, is there on Mars. But one of the ways that primitive bacteria on Earth survive when they're buried miles down beneath the surface is by using chemistry to generate their food. And the chemistry they use is when different minerals have these different states of oxidation. They can sort of use that difference to generate their energy they need to live. So finding that these two different minerals, these two different types of oxidation states exist together could have provided that food source. So we had our checklist of ingredients of life, water, and source of energy. We could check each box. And that's what led the team to think that this was a potentially habitable environment. So finally, I'll just end with where we are now, because we need to kind of wrap it up soon. Mission's going great. We did turn around, finally, on July 3rd. The team spent months at Yellowknife Bay, months longer than we had planned, partly because it was so fantastic, and every time every layer we uncovered, and every more detailed study we did, it got more and more interesting. So we wanted to stay there, and it was worth it. And then, of course, the other aspect is that this rover is just kind of hard to operate. It's a beast, and it's very complex. And our sort of pre-landing notions of how long it would take to drill the first time and that sort of thing, probably everything doubled. And that's fine. That's just how these things work. And yet now, we're ready to do it a lot faster in the future. But it's been an incredible learning experience. That's why it's exhausting. we troubleshoot a lot. We really ask this rover a lot, and the rover always pays off in the end. So what are we doing now? Here's where we are now. Bradbury Landing. We drove over to Yellowknife Bay. Now we've driven well past our landing site and are headed towards Mount Sharp. So we're just a little ways into a long journey, to be frank. We're probably going to arrive there around next summer. So it's still a ways off, and then we'll spend the next years after that, hopefully, climbing the foothills of Mount Sharp, going through those clays and going through those sulfates, looking for how this environment we saw at Yellowknife fits into the bigger picture of Mars. On the way, we take a few pictures. This is a picture we took with that wonderful arm-mounted camera without even deploying the arm. The arm just kind of sits on the rover deck, and we snap a picture every once in a while. Postcards along the way. Look at that. I mean, this is like mind-blowing. These are fantastic pictures of the foothills of Mount Sharp taken by our telephoto camera. Here's where we're going to go. We're going to drive across these dark dunes and then begin driving up one of these canyons. The clays are down here. The sulfates are in these buttes. And then this is that dust layer on the top. And then this is actually where we're going. We're going to this part of the mountain, and we'll drive up one of these canyons up to about maybe here. And in fact, I don't know if you can see it, but there's a sort of a boulder over here, and that'll be the size of Curiosity. So this will be unlike anything we've ever done on another planet. We'll be driving through these mountains and foothills and seeing walls of rock on either side of us. It's going to be fantastic. So I'll just end making sure that you realize how many people contributed to everything that I talked about today. And thank you for your support. So there's a microphone here. We can answer a couple questions live. Then we're going to shut down all the taping that's going on for everybody to watch it. Then I'll feel free to answer more questions afterwards. So a couple questions from the mic now would be great.
You talk a lot about how you've shown that there's a habitable environment. What was there in the past? I think my question is a little different than that. To what extent has the analysis you've done show that you have soil there? Maybe some of what you found is soil that that would support life brought from Earth. You could bring the Earth bacteria and seeds and grow a crop.
Right.
How close are you to showing that is possible? I mean, you'd have to have like a greenhouse and keep the water from escaping and so on.
Yeah, that's not something we directly have thought about. But finding the extent of that heavily oxidized layer on Mars, the fact that if you dig down, even into the insides of rocks, you can get soil that's a lot less toxic to life, is a big conclusion of Curiosity. What future missions are going to do is actually try to drill 1 or 2 meters down to get even further away from the destructive environment at the surface. So I think we're learning that there is raw material on Mars that could provide a less toxic environment than the surface.
So the surface is toxic not just because of the radiation coming in, but because of the chemicals you have in.
That's right. The chemicals that are formed by the radiation also are toxic.
Okay.
I have a two-part question. First off, regarding Marty, were there any fluctuations noted in the descent imager when it reached its proximity? And secondly, regarding solar conjunction, is the rover able to receive any information regarding the instruments on it at the current time?
Right. So we went through solar conjunction, I think, in about April or May. So we actually had to not operate the rover for about, I think it was about 28 days or something, where we were not in communication with it from Earth or from the orbiters. Well, the orbiters actually did talk to the rover, but the Earth could not talk to either the orbiters or the rover. So that was a nerve-wracking time earlier this year. And what conjunction means is that Mars goes behind the sun as seen from Earth, and that disrupts our ability to communicate. So we gave the rover 28 days of things to do, actually, simple things, didn't ask too much, and it did them every day, and we recovered it afterwards. And with MARDI, the descent imager, I don't know exactly what fluctuations you are asking about, but we did record all the different sways of the rover as we're flying down, and then the rockets came on, and it got very smooth. While we're on the parachute, in other words, we swung a little bit. Once the rockets fired, it was a very smooth descent.
Did the descent imager then decide on a proximity that was very smooth and eliminated perhaps other proximities that weren't?
Oh, I see what you mean. You can consider this flight of MARDI as sort of a test run for that. So we ran MARDI, we just turned it on and recorded a movie. But we didn't use the movie in real time to aim for a better landing site. Future missions will do that, for sure. And MARDI is sort of a good test run to do it without putting the mission, online for that.
Thank you.
You're welcome.
Okay, thanks for the presentation. So I have two questions, and then one question is, so what's the best theory so far that explains how water disappeared on Mars? And the second question is, so how can you actually control the curiosity on the Mars? So specifically the localization and also some sort of path planning method they use for the curiosity to explore the Mars. Yeah, that's my question.
Okay, I'll answer the second one. I'm just realizing it's 8 and I have sort of a hard cutoff, but then I'll stick around like I said. Okay. But the second one is Okay, I've just been informed that we have more time, which is great. Now I have to remember your first question. But the second one, I'll get to. We do path planning based on what we call our navigation cameras. So we have a set of stereo cameras that take three-dimensional images in black and white, because that's all the rover really needs. And they're mounted up on that mast. We also have what are called hazard cameras, which are much more fisheye cameras that are mounted down low. So every day the rover sends back those images, and engineers here on Earth put on their 3D goggles and they choose a path. And the current way we drive is actually, we drive to the edge of that 3D map that we can make on Earth. And then we stop the rover and we do it again the next day. Pretty soon, we're going to bring online a capability called auto navigation, where the rover will actually take those images every few meters and figure out its own path. With this rover, there's so much to do and so much complexity, we sort of ramp up, and we're not there yet with the auto nav. The first question about how fresh the water is?
So how water disappeared on Mars?
What's
the best theory we have so far?
Yeah, I mean, the main theory is the one I mentioned, where the solar wind, particles from the sun slowly strip away Mars' atmosphere. As the atmosphere shrinks, both carbon dioxide is being lost and water, but also, more importantly, once you get too thin of an atmosphere, you no longer can support liquid water. The water starts going directly, it's like dry ice on Earth. It goes directly from the frozen state to the gas state. Once that happens, it gets locked up in the polar caps. If you're actually to melt Mars polar caps, you'd get several meters of water around the planet. You get an ocean, basically. But right now, all that water is locked up at the poles.
Okay, thanks.
Mm-hmm.
Hi. This isn't a very scientific question, but I heard the other day that the budget of JPL is going to be less on space exploration and more earth sciences, and I was wondering if that's going to affect you, and if the project, and if the sequester has affected the project.
I don't think that there's going to be a decrease in what JPL does in terms of planetary exploration. I mean, we're still waiting for some guidance there on what the big missions will be in the future. We of course have the 2020 rover mission that was announced, so follow on to Curiosity. Hopefully we'll see an Outer Planets mission come pretty soon, hopefully to JPL. And then of course we do have a really vigorous Earth exploration program here as well, which I think it will be the near-term emphasis, just because there's sort of a gap in. We just got Curiosity there, but I think overall things are pretty healthy. And the sequester, I don't want to comment.
Okay.
It's a pain for everybody in the country.
Yeah. Okay. Thanks.
Mm-hmm.
Congratulations. It was just so, I wanted to jump up and cheer many times during that movie and other things you've said. Thanks again, and to everybody involved. So the selection of Mount Sharp, again, it's because it has the most sedimentary record, which would be the most useful thing to try to read.
Mm-hmm.
I see. And I know the main thing you said was to see whether Mars was ever inhabitable, but can you foresee that any kind of discovery here or understanding could also contribute to our understanding of the origins of the universe? Any
question.
processes or elements or anything like that?
Yeah, it's an interesting one. I think our instruments are capable of studying the more primitive rocks of Mars, which would be the kind of thing that would tell you more about how the solar system formed, for example. The interesting part of it is we're sort of avoiding those rocks, because the more interesting rocks to us are the ones that have been taken from their primitive state, and other minerals have formed from them because of their interaction with water and other processes. So, we actually, if we were to see a chunk of primitive Mars basalt, we would probably skirt around the outside to keep the people on our team who are interested in those questions from getting too excited.
But you never know what you're going to find on the long trek to Mount Sharp either, right?
That is true.
Because all you have so far is things observed from higher up.
Yeah, I mean, okay. in about a half a kilometer, we saw 5 different rock layers, only 2 of which we expected to see. And, there's so much more left to go to Mount Sharp. That's actually one of the biggest problems on the mission right now, is keeping our blinders on. We want to get there. And like I said, it's a year away. And the more we stop to look at stuff along the way, you're never going to, we make all these analogies all the time. Like, you got to keep the kids inside because you want to get to Disneyland eventually. You can't stop at the dinosaur on the side of the road, and yeah.
Yeah, again, that was a really great video. I really enjoyed it. So we found all this evidence for liquid water on Mars, and I'm pretty sure, I don't know if it's the same on or different on other planets, but different environments, but water freezes at 32 degrees. So do we have any idea what temperature Mars would have been to host liquid water?
Right. Yeah, so that turns out to be a pretty hard lower bound on water freezing at 0 degrees Celsius or 32 Fahrenheit. And that would have been true on Mars, really independent of how thick the atmosphere was. What changes is actually the boiling point. And so on Earth, it's 100 C or 212 Fahrenheit. When you get a very thin atmosphere, it goes all the way close to 0. And like I mentioned, it behaves like dry ice at that point. It goes from solid to boiling right away. So if you were to throw out a bucket of water on Mars' surface today, it would sort of freeze and boil away at the same time. Kind of interesting. And rivers won't flow very long because they will freeze and evaporate at the same time. So to answer your question, you would have had to have parts of Mars above 0 C or 32 F to have liquid water.
Okay. And the second question, if you don't mind. Mm-hmm. In one of your prior, the previous slides, the snapshots from Mars, the one where you showed Curiosity would be the size of this. How far away is that, and how far up Mount Sharp is that?
Oh, this guy. So what I mentioned about where we'll be in a year is to what we call the Mount Sharp entry point, which is sort of over here somewhere. And that's about, roughly 5 or 6 miles. So, yeah, it makes us sound bad, right? 5 or 6 miles in a year, come on. But yeah, there's no road. And then it'll probably take us, then we're going to actually start drilling again and things like that as we go to these layers. So if we were to just, and then this is probably another few miles to get from the entry point up to the dusty layer. But of course, this part's going to be much slower because we're going to do a clay drill, at least one, probably a lot, sulfates, and then get up here. So, yeah.
How far up the mountain is that?
Up to the dusty layer is actually, it's only a few hundred meters up at its lowest extent. So we don't have to actually climb that high, but it's a lot of lateral driving. I mean, I didn't really mention this, but being 3 miles high, Mount Sharp is higher than any mountain in the United States, except for Alaska. So it's a high mountain, and even going up the foothills of it is challenging.
Cool. Thank you very much.
Hi, congratulations, and thanks for sharing. I wanted to know a little bit about the communication with Curiosity. How do you guys communicate? How long does it take to get it to answer and do things?
Sure. No, that's a fun one. So we have what's called the Deep Space Network here on Earth, these big antennas. I'm looking for one around the room. I think it's in the museum. You can see it. But they're these giant antenna dishes. And there's one in Australia, one in Spain, one in the US. So no matter where Earth is rotating, Mars is always in the view of one of them. But then, of course, Mars is rotating also. So the rover comes in and out of view from Earth. So we use the Deep Space Network to give the rover a set of commands once a day. As Mars just comes into view and Earth is rising on Mars, we give it a set of commands. And actually, it's really when the sun is rising on Mars, at about 10 a.m. or so on Mars. And Mars has a 24-and-a-half-hour day. So it's very similar to Earth in that respect. About 10 a.m. on Mars, we send up a day's worth of commands. The rover does that day's worth of commands autonomously. We can't really joystick it from Earth because it's about a half-hour round-trip time if we were to try to turn left and then wait half an hour. We don't do that. So it does a day's worth of commands, and then at 3 o'clock in the afternoon or so, Mars Reconnaissance Orbiter flies overhead, and for about 15 minutes, the rover communicates with it and sends the data back. So once a day, we command it. Once a day, we get the data back. And we can do that every day for about, this is where it gets a little tricky, for about half the month, because that's when our 24-hour cycle is lined up with Mars' 24-and-a-half-hour cycle. The other half of the month, that timing no longer works out. So you have two options. You either start living on 24-and-a-half-hour days, which we did for 3 months. So yeah, again, thank you. About this many people lived on what we call Mars time for 3 months. I did too. It was horrible, but very productive. And then we got off of Mars time, which means that for half of the month, we can sort of do things every other day.
Thank you.
Mm-hmm.
Hi, thank you. Follow-up actually to a previous question. What can you really say about the climate that would have been present 3 billion years ago to produce that kind of a river? Would it have been snow melt, snow runoff? Would it have been rain? Where did the water flow? Where's the ocean or lake that it flowed to?
Right.
What kind of climate was there? And if you can describe that, how do you know?
Yeah. Whew. That is one of the, other than life on Mars, I'd say that that's probably the number one question, about Mars exploration, is how did it get from a planet that could have had these big rivers and even catastrophic floods and this stream bed to the planet that is today that you can't even support a drop of liquid water on the surface. And we have these theories about the atmosphere being lost, but we don't really know much more of the picture then. Say you had a thicker atmosphere, if it wasn't warm enough, like the other gentleman pointed out, you still would have a lot of frozen water and a very limited hydrologic cycle perhaps. There could be some kind of climate where it may be, one thing is CO2 is a greenhouse gas. So some theories involve getting a thicker atmosphere, getting more warmth, and then having that allowing it to be warm enough for liquid water. That's not a home run. It turns out there's issues that come up when you have so much carbon dioxide. But the other things are the ones you mentioned. In order to have a hydrologic cycle with like rain, you really have to have a big body of water somewhere for it to evaporate and then be transported and then rain somewhere else. That could have happened, although there's not a lot of evidence for the kinds of really finely braided streams like on Earth that happen when rain falls. Instead, we see a lot of rivers that seem to start out of nowhere and flow vigorously and then end. Very mysterious. But another option, like you said, is snow. So even today, the water does go from the vapor to the snow phase and back and forth. And it could have done that in the past in a much more vigorous way. It could have had big snowpacks, and the bottom of those snowpacks might maybe melted and formed the start of these rivers. We don't really know. We're going to hope to find some of that in these layers of Mount Sharp.
Thank you. I also thank you very much for a great presentation. What's the future of this particular curiosity? Where does it end up? How long will it last?
Yeah.
And what happens in the end?
We hope it lasts up to that dust layer. Now, Spirit and Opportunity were also built here, of course, and built to a lot of the same standards as Curiosity and use a lot of similar parts. So, we can go off of their lifetimes a little bit, and when we're thinking about this, and I think their Spirit lasted at least 7 years, maybe 8, and Opportunity is going on to 10 years. It's still alive today. So there's 2 rovers on Mars today on opposite sides of the planet. So we hope we can last that long. We have some advantages in the sense that we were built to be even a little bit more robust than Spirit or Opportunity. We were built with a little better warranty in that respect. But we also are subject to all the same things that destroy beautiful mechanisms once you put them on another planet.
He kind of took my question.
Okay.
But do you guys have any specific plans as where Curiosity is going to go after Mount Sharp?
Yeah. I don't think there's going to be an after. Don't tell the rover. So actually, what we hope to do, this is going to be a gold mine. From everything we believe, this is going to really tell us a lot about the environment of ancient Mars. We found this one specific lake, we think, at Yellowknife Bay. There could be a similar habitable environment at many different levels of this mountain, and each slightly different, and maybe even a story of better ones at the bottom, getting worse as you go up. All those things could happen. So not only are we going to be here several years, but say we sample all these layers and go all the way up to the dust, and we create a story. I guarantee the first thing scientists want to do is make sure they're right, so they'll drive over here and do it in reverse on the way down. And actually, that's the right thing to do scientifically. So, we plan to explore this as long as the rover talks to us.
Thank you and good luck.
Thank you.
So my question is related to what if something breaks on Curiosity?
Okay, yeah. We worry about that all the time. One thing that's pretty cool is that the rover is smart and protects itself, and it even protects itself from us. So the rover has a lot of software. I think it's over 500,000 lines of computer code. So more than any one person and even hundreds of people could write. And a lot of that software that's on the rover is what we call fault protection. We want to keep it from faulting. And a fault could be anything. It could mean bumping into a rock. It could mean using its arm and hitting itself. Or it can mean running one of the ovens in the SAM experiment too hot so it melts. And to protect the rover from us, that software on board checks everything we ask it to do. And you probably won't know, but your parents will know. I'm sorry, Dave, I can't do that. Right? There's a computer that tells a human that, and the rover will tell us that sometimes. That's sort of the good news, is that it's a little hard to break the rover because the rover is smart enough to keep us from breaking it. The bad news is that things will break just because there's so many moving parts. All the wheels have motors, and they were lubricated before launch. You can't lubricate them anymore. So once those things start wearing out, a wheel might stop. So we've designed a few things to sort of extend the life. We can drive with only 5 wheels, for example. And in fact, Opportunity and Spirit, I think both ended up losing a wheel and dragging a wheel. We actually learned from that and made it so the wheels don't freeze. We won't have to drag it, in other words. It'll just rotate. Part of the fun of having 6 wheels is you can still drive with 5 of them. And so there's things like that. But one thing we can never do, I got to tell you one more thing. One thing we never do is replace anything, of course. But the other thing we do is we have 2 of a lot. So we actually have 2 pairs of navigation cameras. We use one now. We have a backup in case the prime one fails. And we have 2 computers on the spacecraft. So the entire computer, the entire brain of the rover can get fried, and we can switch to the other one. And in fact, we did that once already during this mission. So those are all the ways.
Thank you so much.
You're welcome.
So I love these pictures during the daytime like everybody else, but something that I didn't expect and that I really enjoyed is seeing the pictures of Mars's moons.
Right.
And pictures of the sun taken from Mars. And I didn't even realize that was something that you guys were going to study. And I just saw recently you guys took a night picture in ultraviolet light. And I was just wondering if you had any plans to take maybe like a long exposure of the Martian landscape at nighttime. Like I potentially get public interest to see that, like star trails and just something that I personally would like. But I was just wondering if there were any scientific merit to something like that.
That's the key, actually. You gotta find the science reason to sneak the cool thing in. But yeah, if you look at JPL's homepage today, just today we released some images of Mars' 2 moons, Phobos and Deimos, as taken from Curiosity. And they are actually scientifically valuable because those moons orbit very closely and are affected by the shape of Mars and actually what Mars is made of. Whether it has what the distribution of stuff inside Mars is affects the gravity that those moons feel. So by tracking those orbits very precisely of Phobos and Deimos, they kind of trace out the shape of Mars internally. And so we take these cool pictures, but they're good for science as well. And the one that's on the homepage today is the first time we ever saw Phobos, the big moon, pass in front of Deimos, the small moon. So it's called a mutual occultation or something like that. I'm not an astronomer. So those are useful scientifically. The images of the sun we take once a week or so are actually very useful because that's how we tell how much dust is in the atmosphere. So on Earth, when you think of weather, you think of sort of wind and water. On Mars, you think of wind, water, and dust. There's always some level of dust in the atmosphere. And by studying the amount of dust, you can sort of figure out how storms are working and that sort of thing. And so we take pictures of the sun because we know how bright the sun is. And when there's dust in the atmosphere, we can very precisely measure how much dust there is by the decrease in sunlight. I think that's, the star trails one. I just heard that, I heard our camera team talking about that. It's hard because there's not like moonlight. So to take the landscape images at night, it's too dark. There's really nothing lighting it up. Phobos is not big enough. But star trails we might be able to do. There isn't really good science for that, though.
Awesome, thank you.
Okay.
Hi, you kept talking about this theory in which there was an ocean on
Yeah.
Mars at one point. Where did that come from? What's the reasoning that you might discover something like that now? Where did that come from?
It's a few different things. There are actually some, I think one of the two sort of things that really hint at it are there's a whole lot of huge rivers and even floods that start up high and end up low, and then you can't really see where they end. It's almost as if they went into a larger body of water. Couple that with the fact that Mars has this very interesting shape where most of the southern hemisphere of the planet is a few miles higher elevation than the north. So the north is a big basin. And there are actually some scientists who are tried to trace around what they think are shorelines of an ancient ocean. So it's all kind of circumstantial evidence at this point. We don't know for sure there was an ocean, but there's a lot of reasons to think there could have been because we see a lot of water that must have moved from the high elevations into something in the low elevations that's in a closed basin that could have filled up with water.
And do you ever think another rover may join Curiosity in this mission or not?
It's possible. We only do these things every decade or so because they're so complex and it takes a lot of time to kind of get the next generation of rover and instruments and everything. So in 2020, there's plans to launch a Curiosity-like rover, but to actually have it go around and collect samples of rock that would actually get brought back to Earth at some point by a future mission. And if we continue to find that this is not only a habitable environment at Yellowknife Bay, but this is the best place to take those samples back to Earth and using even better experiments, the 2020 mission might come here.
Thank you.
All right. So in my opinion, one of the cooler things about this rover is the power source. So what kind of went into the decision to not have solar panels like all the previous rovers? And how does it work out in terms of cost versus longevity and that sort of thing?
Sure. Interesting, because we've learned over time, and I think 10 years ago you would have gotten a different answer. So 10 years ago, the idea was that Spirit and Opportunity were built to last 6 months, maybe, and so their prime mission was thought to be able to be accomplished in that amount of time. So all they had a requirement for was to last 6 months. So solar panels for 6 months work great. They provide a lot of power, and then as they slowly get covered by dust, it's okay, because in 6 months, you'd still have enough power. Of course, I just told you Opportunity is now going on 10 years. So 2 things happen. One, Opportunity is living on a lot less power than it had in its heyday. So it's eking by. But the better news is that there's been what we call, scientific term, wind events, because we don't really know what they are. Are they dust devils? Are they gusts? Or what are they? There are wind events that have cleared off the solar panels of Spirit and Opportunity many times and given them sort of a new lease on life. So we didn't know that. And so by the time Curiosity was already well into its design phase, we had already decided for a 2-year mission, which is what Curiosity's warranty is. We didn't want to do solar panels. 2 reasons. One is that we have a much bigger rover, a lot hungrier power-wise. So we would have to carry these enormous solar panels that would have made it hard for us to drive. We would have needed a lot more area than Spirit and Opportunity because we're so much bigger. The second one is, for a 2-year mission, we didn't think we could last on solar panels, but we didn't know about the wind events yet, and we couldn't guarantee them at Gale Crater. So that's why we ended up with what we call a radioisotope thermoelectric generator. I don't want to harm these nice people here, so I'm not going to use my laser pointer. But behind these guys over here, you can see these little garbage can things on the end of Voyager, right in front of the couple there. And they are actually, I can see 3 of them, I think. 3 of them kind of strapped together, powering Voyager. And Voyager's still talking to Earth today. So when you use radioisotopes, naturally decaying radioactive material that you put in a well, I shouldn't say garbage can, but that kind of structure, and then you generate electricity from the heat it gives out, they can last a long time. They'll outlive Voyager, and they'll outlive Curiosity as well.
All right. So for example, for the 2020 rover that might do something like storing samples for sample return, would you be considering making a replaceable power source, so whatever comes in to do the sample return could give it a sort of longer lease on life? Or would that just be too expensive? I don't know.
Yeah, I hadn't thought of that. I don't think that rover needs to necessarily be alive. They can just store the samples and the next one comes and takes it. But I'm sure they're thinking about all these options. Cool. The RTG, the radioisotope thermal generators, worked great for us, and I think it's going to be flown on future missions as well.
You do awesome work. Thank you so much.
Thank you. Okay, great. Oh. Pardon me, I want to take one from the people watching online or through social media. Have you ever found any more hematite blueberries in this area, similar to those found by Opportunity? So Opportunity found a lot of little round, what they call blueberries, which are little round stones, I guess you call them, made of a mineral called hematite. And that's what attracted them Opportunity to that landing site. It was a place where there's a big signature from orbit of this mineral called hematite, which could form in the interaction with water with rock. We haven't found those specific hematite minerals, but we did find these nodules I briefly mentioned, the pimples that were covering the rock. It's a kind of a similar thing, where water flows through rock, leaves hard minerals behind, and then as the rock erodes, these pimples sort of come out because they erode less well than the rock around it. So that's that one. I'm going to knock off this other one really quickly. You mentioned that argon was found to be the second most abundant gas. What are the chances of it being found planet-wide? That's an easy one, because the atmosphere, like on Earth, blows around. So anything we would measure at Curiosity is at least regional. It's definitely not restricted to just where Curiosity is. unless we happen to find a volcano going on right next door, which isn't the case. So we believe the argon and nitrogen that we're measuring are indicative of the composition planet-wide.
Hi. So you pointed out a few times that Curiosity moves very slow. So what is the speed and what was the biggest limitation that you had, from the engineering point of view, that you had to limit the speed?
Sure. Limiting the speed is really safety. So we drive so that we don't put any forces on the rover that the rover can't handle. The faster you drive, the harder you hit something, that sort of thing. And the harder your wheel might fall off a rock if you're driving over a rock and the wheel slips off it. So we drive slow for that reason. We also drive slow because we're taking images every now and then to create new maps of the hazards around us, especially when we go into this auto navigation mode. So those are the reasons we drive slow. And the driving slow means much less than 1 mile an hour. So we drive about a football field a day. And, it sounds horrible, and it kind of is when you're doing it. But when you consider that if you were at the end of a football field and you had binoculars at eye level and you were trying to see if there was any hazards, you can imagine by the end of the the end zone, you wouldn't be very confident that your quarterback isn't going to hit a sprinkler head, So we drive to the end of those images at about 100 meters away. One more question, then I got to wrap up.
Just still one leading question.
Okay.
Is it possible to make it go faster based on the terrain that you observe?
Yeah, I mean, we don't make it go faster, but we interrupt it less. So when it's smooth sailing, we actually do what's called blind driving. We just tell the rover, go put the pedal to the metal, don't even check for obstacles, because we've already certified the terrain's flat. So that's the fastest we can drive. Last one.
So about the comet that's supposed to, that might hit Mars next year, how are you guys preparing for that? Or is that something you're even worried about?
It was interesting when we heard about it. But it turns out that this comet called ISON, I-S-O-N, I have no idea what that stands for, is not going to hit Mars. So now that we are tracking it more, we being the global we, not me, we know that it's not going to hit Mars any longer. In fact, I kind of heard depressing news that it's fizzing out. But hopefully it won't fizz out, and then we will actually attempt to image it. Both Opportunity and Curiosity will image it, hopefully, from the surface. That's it. Thank you.